All right, guys, here we go. We're going to start in chapter 17, Organic Chemistry. So today is section 17.1, and we're going to be looking at properties of organic and inorganic compounds. And then we're going to be writing names and drawing formulas for compounds called alkanes. As we have learned previously, organic chemistry is the study of carbon containing compounds. The element carbon has an important role because there can be many carbon atoms bond together in a vast different array of compounds. We can have lots and lots of different arrangements of atoms, and the arrangements give different properties. Organic compounds always contain carbon and hydrogen, and sometimes other nonmetals like oxygen, sulfur, etc. We find organic compounds in many places that we see every day: gasoline, medicine, shampoo, plastic, perfume. Lots of compounds are organic. The food we eat is composed of organic compounds, carbohydrates, fats, and proteins that supply our body with the energy and the atoms needed to repair our cells. Here we have some typical properties of organic compounds: low melting points, low boiling points. They are not soluble in water and typically are less dense than water. So, an example of a organic compound, which would be vegetable oil, is a mixture of organic compounds that doesn't dissolve in water. Many organic compounds, again with properties of them, will undergo combustion and burn vigorously. In contrast, inorganic compounds, those would be compounds that don't contain carbon, typically have high melting and boiling points. Many inorganic compounds are ionic, and ionic compounds we know are usually soluble in water, and most do not burn. Here we have two compounds. We have propane and sodium chloride. Propane is organic. It's composed of molecules. You can see the individual propane molecules here. And then sodium chloride is an inorganic ionic compound composed of many ions in a repeating crystalline pattern. So comparing these two compounds, here we have the propane and the sodium chloride. The organic compounds contain carbon and hydrogen, sometimes other other nonmetals. Particles are made of molecules. Bonding is covalent. Bonds are typically nonpolar. Low melting point, low boiling point, flammable, and not soluble in water. So those are some summary of some organic compounds properties. Sodium chloride is inorganic, also ionic, so made of ions with ionic bonding. Some can be covalent, but most are ionic. We can have a few polar covalent, a few non-polar covalent in inorganics, but most are ionic. Much higher melting points and boiling points, does not burn, and is soluble in water. So we can see the differences between the propane organic and sodium chloride inorganic. Hydrocarbons are organic compounds that contain only carbon and hydrogen. If you draw the electron dot formula for hydrocarbons, each pair of electrons is a single covalent bond. We call this a saturated hydrocarbon that contains only single carbon-carbon bonds. Because it has the maximum amount of hydrogens possible, it is saturated with hydrogens. And expanded structural formulas drawn shows us the bonds between all of the different atoms. So just some background information here. Methane is the simplest organic compound. It is a single carbon atom with 4 valence electrons shared with 4 hydrogen atoms, each with 1 valence electron. So if we were to draw the dot structure, it would look something like this, with a pair of electrons shared between the carbon and each hydrogen, and then the structural formula showing the shared pair of electrons as a bond. In methane, the covalent bonds between hydrogen and carbon are directed toward the corners of a tetrahedron. So there are always going to be 4 bonds between each carbon atom, and they arrange themselves in this tetrahedral shape that you can kind of see particularly in this ball and stick model. There are different representations that we can draw, and you need to be able to draw some of them. If we were in class, we would have models. We would look at the space filling model and the ball and stick model. The ball and stick model really gives us the tetrahedral shape, and it lets us to kind of visualize the bonds. But we know in reality the atoms actually have to be close enough in order to overlap their orbitals. So the space filling model is really as close to reality as we can get. But the ball and stick model shows us the bonds more clearly. The wedge and dash model attempts to draw on a flat surface a 3-dimensional shape. The wedge shows that this hydrogen is coming toward you, and this dash shows that this hydrogen is going away from you behind the paper, and these 2 hydrogens are in the plane of the paper. So this one's coming out toward you, this one's going backwards away from you, and that's called the wedge dash model. The expanded structural formula just shows the carbons with all 4 bonds and all 4 hydrogens. It doesn't really show the tetrahedral 3-dimensional shape, but it does show the carbon and all the bonds. And then this is called the condensed structural formula, just the carbon and the hydrogens, not showing the bonds. The next most complicated hydrocarbon is called ethane. It has 2 carbons surrounded by 6 hydrogens, and each carbon gets 3 hydrogen atoms. So this is the next simplest hydrocarbon. So in the space filling model, we see the 2 carbons real close to each other, and the hydrogens real close to the carbons as well. We can visualize the bonds a little easier here with the ball and stick model. We see 2 black carbons and then 3 white hydrogens and 3 white hydrogens on the end. The wedge and dash model, again, showing us the carbons that are coming out toward the paper, then the dashes showing the carbons that go behind the paper, and then these hydrogens and carbons would be considered in the plane of the paper. The expanded structural formula, this is the one we'll use the most, showing the two carbons, each having 3 hydrogens around it. Then the condensed structural formula showing the bonds between the carbons, but not the actual bonds between the hydrogens. The group of compounds we're talking about today are called alkanes, and they are compounds that contain only carbon and hydrogen, and they are connected by single bonds. So that's the main key there, is an alkane contains single bonds. Ethane contains 2 carbons. Propane contains 3 carbons. And butane contains 4 carbon atoms, all connected in a row, or what's called a continuous chain. The smaller alkanes are named methane, ethane, propane, and butane, with 1, 2, 3, and 4 carbons, respectively. And the naming system is named according to the IUPAC, the International Union of Pure and Applied Chemistry. That's the naming system that we'll be using. Alkanes that have more than 5 carbon atoms are named with the prefixes that we have learned previously. Penta means 5, hexa means 6, hepta, octa, nona, and deca. So those all increase the carbon atoms 1 each. So these are the names and formulas of the first 10 alkanes. So we have methane with 1 carbon atom, 2 carbons is ethane, 3 carbons is propane, 4 carbons is butane, 5 is pentane, 6 hexane, and so on down the line until we get to 10 decane. So looking at the condensed structural formula, notice that the ends each contain 1 carbon surrounded by 3 hydrogens at each end, and the carbons in the middle, because they have a carbon on either side, there's only room for 2 hydrogens to make that total of 4 bonds. So there's CH2s in the middle and then a CH3 at the end. Over here what's called the line angle formula, and we'll talk a little bit more about that in just a little bit. So here we're going to draw a molecule of pentane. Pentane, of course, penta is 5. So to begin with, you want to draw out 5 carbon atoms in a continuous chain. So just like this, 1, 2, 3, 4, 5, a single bond in between each carbon atom. Then we're going to draw what's called the expanded structural formula, and then we're going to add hydrogen atoms using single bonds to each of the carbon atoms so that each carbon atom has a total of 4 bonds. The carbon-carbon bonds come first, and then the hydrogen. So these carbon-carbon bonds come in first, so there's 2 bonds, so then 3 and 4. So this would be what we would call the expanded structural formula of pentane. You can draw the condensed structural formula by combining the hydrogen atoms with each carbon. So instead of drawing out 1, 2, 3 hydrogens, I would just write CH3, indicating that there's 1 carbon with 3 hydrogens attached to it. Then I draw the bond between the carbons, and then I see this carbon has 1, 2 hydrogens, so I write CH2. Then I draw the bond between the next 2 carbons, and this carbon again has 2 hydrogens. I draw the bond. This 4th carbon has 2 hydrogens. And then the 5th carbon has 1, 2, 3 because it's an end carbon, and it has CH3. So this would be known as the condensed structural formula. The line angle formula is a super condensed version of the alkane, and we draw a zigzag line, and the end of the line and every corner of the zigzag represents a carbon atom. So we don't write any letters, we don't write any carbons, we don't write any hydrogens. We just represent, so this end represents carbon number 1, this angle represents carbon number 2, this angle represents carbon number 3, this angle carbon number 4, and this end then carbon number 5. So that would be the line, so this would be considered the line angle formula.